Our first speaker this afternoon is Morgan Brown from University of Miami, and his title is Birational Geometry of Moduli Spaces via the Essential Skeleton.
Okay, thank you for the introduction and for the opportunity to speak here. So a lot of what I have to say here is, it's not going to be like a lot of, theorems in this talk of new stuff, but, some ideas and some work in progress. So let me start off by introducing some concepts. So this is the dual complex and essential skeleton. Well, of what? Well, I'm going to get to that in a minute. And so the idea here is we're going to start with, x delta, a pair. And we're going to assume, in general, what you have here is something like x is, projective, and this is, you want to think of this as like some space, and then this is the boundary, and so the complement of delta and x is some open set that we're particularly interested in. But, just for the moment, let's say that x is normal, and I want kx plus delta q Cartier. And this is, this is the setup that we need to be able to meaningfully talk about discrepancies if we want to define singularities in the minimal model program. So I can then consider a log resolution of x delta. Let y gamma be a log resolution. And so then we'd have f from y to x. And the idea is that, in this notation, gamma itself, it's a log resolution, so it's all the exceptional divisors as well as the strict transform of delta, and then you just assign everything coefficient 1. This is kind of the, the standard way just to present your log resolution. And in particular, this being a log resolution means that gamma itself has normal crossings. So because gamma has normal crossings, we can define the dual complex d of gamma. And the idea is that this is just the intersection complex when you think of, this gamma is a sum of irreducible divisors, and they have intersections. And so then this dual complex is just keeping track of that combinatorial data in the following way. So then you have like I simplices. So dimension I simplices of this complex. These are, tautologically in one-to-one correspondence with the codimension I strata of gamma. Okay. And so this is, the sort of thing that shows up a lot in algebraic geometry is that, you want to understand not just varieties, but pairs for various reasons. One of them is, because you have this setup where you're looking at resolutions of singularities. And then the context that I'm building towards today is where x is some compactified moduli space, and delta is the boundary. So in particular, the example I'm really going to have in mind eventually is where, right, maybe off to the side, like x is m0 n bar, and then the boundary delta is just the boundary of, m0 n bar. So here, this is all of the, stable n-pointed rational curves, and then these are the ones that are actually not smooth, where you actually get 2 points colliding, and so you get a bubbling off of one of the curves. Okay, so back to this story. So what I want to emphasize right now is the role these dual complexes play in birational geometry. So in birational geometry, when you have this situation of a log resolution of a pair, and you have that kx plus delta is q Cartier. Well, the reason I require this condition is because I want to pull back kx plus delta and compare it to the log canonical divisor ky plus gamma on the other side. And so this is, the typical discrepancy calculation. You get ky plus gamma is equal to f upper star of kx plus delta. And then these have to agree pretty much everywhere except on the components of delta and on the exceptional divisors, which are just the components of gamma themselves. So then I can put on the other side, I have plus alpha I gamma I. And so then the idea is these alpha i's control how bad the singularities of my original pair were. Okay, so these alpha i's are the log discrepancies.
So gamma is the proper transform, strict transform.
Well, it's the strict transform of delta and then plus the exceptional divisors. So, I mean, if it's like,
Gamma I is not exceptional.
well, it might be one of the delta i's. So the gamma i's, they're either exceptional or they're components of the strict transform of delta. I mean here the alpha I for delta, it's just it's just like 1 minus the coefficient in delta there. So often those you don't really have to think about, but it's just to sort of get a uniform definition. We consider them both at the same time. Okay, so the alpha i's, these are the log discrepancies, and so the idea is that the log discrepancies in the middle of a model program, you really want these log discrepancies to be positive. So you have good singularities when they're positive, and then you have bad singularities when they're negative, and then in the middle, this is sort of like the edge case when they're 0. Those are where where you sort of hit being exactly log canonical. So the thing we care about with these alpha i's for now is just, are they positive or negative? So then off to the side here, I think I can't really use the bottom there. I'm going to just let d0 of gamma just be the subcomplex so of simplices whose vertices have alpha I less than or equal to 0. So this is somehow, I mean, you can think of this as like the non-KLT, this is somehow representing the non-KLT locus upstairs. So like downstairs, you have the non-KLT locus, and then when you take the log resolution, where the pair fails to be KLT is reflected in these discrepancies, which are coefficients, related to the coefficients of gamma, and the comparison of the coefficients of gamma with those of delta. And so if we just focus on the part with the bad singularities, with the full singularities, what we find is that this complex here is actually an invariant of the original pair x delta. So this is a theorem in birational geometry due to Dufresne, Kolar, and Chen-Yang Xu. And let's just say, let me just write it here. So for any 2 log resolutions, y gamma and y prime gamma prime, we have that these complexes are homeomorphic. All right, I don't know if I prepared a symbol for homeomorphic, so let's just say that, just write it in English. Okay, and then in particular, so what is this object, this particular complex? I mean, really, if you take, if what you'd really like to take is you just like to take some DLT minimal model of x delta, which is possible, we know this by, it follows from BCHM. I think the particular result in this case is due to Haken, but, so you can the technology of the minimal model program allows us to actually, in this case, produce a DLT minimal model of x delta. So in particular, that has some nice singularities, and you also want that kx plus delta is nef. And then in that case, the dual complex of that model is exactly one of these. So, and in particular, if let's just say, in particular, this is homeomorphic to the dual complex of coefficient 1 components of delta prime. Let's just say delta prime, where x prime delta prime is a DLT minimal model of x delta. Okay, so all of this is just to say that these dual complexes, they appear in birational geometry in a very nice way, in that, when we're thinking about birational geometry in terms of the minimal model program, what we start with is, we have some variety or some pair. So in this case, I'm thinking about pairs. And then we want to produce a model where the pair is not too singular, and also the log canonical divisor has some positivity condition, like it's nef or it's ample. And so there's, of course, what we've learned is there's a trade-off between this, is that as you make the canonical divisor more positive, you have to introduce more singularities. So, if you wanted to make it ample, you might have to have log canonical singularities. And then kind of in the middle, we're here, kx plus delta is nef, and then we're saying that it's DLT, which basically is saying that the delta, in the important places, it looks like it's normal crossing. So at the places where where the strata, where all the components have coefficient 1, this, there you can it's normal crossing, you can define the dual complex, and it's this nice birational invariant. Yes? Oh, well, if this original guy was KLT, they'd be positive, but I'm not saying this is KLT. So in general, this is going to be, eventually this might be quite singular. That's getting a little bit ahead, but in this case, where delta is just straight up the boundary of something, then this is not KLT just because the coefficients are 1. So here, in this case, you just have, if x delta is just a nice normal crossing pair, and I guess I should say, when I say DLT minimal model of x delta, I mean it's a DLT minimal model over x delta. So you should think of this as like a partial desingularization. So when I'm saying that the log canonical divisor is nef, it's the relative log canonical divisor I'm looking at here. So this should be a DLT, I guess more precisely I should be saying a DLT minimal model of some resolution over x delta. It's really the relative canonical divisor that I want. So in the case where x delta has nice singularity properties, if it's already DLT, then the minimal model is just x delta itself. So, and then this is just saying that what you're saying, which is that, the exceptional divisors, they have positive, the exceptional divisors are supposed to have positive log discrepancy, so you're not getting anything new here. The only way you're getting new stuff is like, your delta looks like this, with coefficient 1 here and 1 here. You blow up this point, and then you have log discrepancy 0 here as well. So then you haven't changed the topology of the complex. The complex you get here is just an interval, and then the blow up at this point makes you subdivide the interval. So you don't get the same combinatorial type, but you get the same topological type. Okay, yeah, good point. Okay, so, all right, so what we really like to say, and this is this is present in their paper already, is we don't want to say these are homeomorphic. We want to say they're the same. But it's like, okay, what do you mean by the same? They're not the same complex because, they don't have the same combinatorial type. So alternatively, we want to say, okay, we want to give some semantics to these complexes. We want to interpret all of the points of them as something so that on one side and on the other side, we do our interpretations, we get the same thing, we can match them up and kind of understand this theorem more intrinsically. And the way to do that is by thinking about valuations. Because when you have when you have this situation where you have a pair, you have a bunch of divisors, then each divisor corresponds to a valuation, just the divisorial valuation for that divisor, and then where they intersect, you get monomial valuations. And you get a lot of them depending on how much you weight each component. And that's exactly what's happening in the dual complex. So this is exactly the picture that happens in toric geometry, and kind of the point of my talk is to say, well, the way it works in toric geometry, you can bring these techniques into other arenas and it still works. Okay, so let's look at this from a valuation perspective. Right, this marker was working. Okay, so what we want to do is we want to interpret spaces like these complexes, so like this one, as spaces parametrizing valuations. And this is often inside the Berkovich analytification of our variety X. Okay, so I'm just going to briefly introduce this with the definition and the example. It's the sort of thing where it's like, well, if you haven't seen it before, then it's I'll kind of give you a taste of what's going on. You just think of this is a space of evaluations. If you have seen it before, then this is kind of one of the standard pictures. But the idea is you have X, you say X is over some K. If we're taking the analytification, we're going to say that K is a field with valuation. I guess in my notes I called it rho because I was, often people use nu and then v for other valuations, and it's like looks too similar. So I have some valuation on the base field, which might be trivial. In fact, later on, this is just going to be, we're going to be looking at the trivial valued case for the most part. And then the analytification of such a variety over this field is each point in the analytification corresponds to a scheme theoretic point of X. And then the valuation on, and I think technically, so forgive me if there's a mistake here, but you take a valuation on an extension of the residue field at that point, and you want it to extend the base field. So we want it to extend the valuation that we fixed here, and then you mod out by some equivalence. Okay, but I mean, this definition, not so worried about that. I mostly just want this to say, well, we want to interpret these dual complexes as living inside some space evaluations, and this is the one I'm using. There's a lot of approaches to non-Archimedean geometry, and well, I use this one because this is the one I learned, but also because the technology that I want to use that sort of merges non-Archimedean and birational geometry is developed here. Okay, so I also want R to be my valuation ring, so it's just the elements with positive valuation, and then given my X, which we'll say, let's say X is some projective variety, we'll just choose a model over R, which is SNC. So the special fiber is SNC inside X. And then what you can do is this complex here, you can so here you have a boundary already because you have the special fiber, and then you can define essentially this guy here intrinsically in terms of the valuation space, and this is what's called the essential skeleton. Okay, so this concept, there's a lot of people responsible for it. The major development was done by Mustad and Nicaise in a paper, but their work relies heavily on a specific case worked out for K3 surfaces by Kontsevich and Soibelman. So they do the case where you have a K3 surface. And then I also should probably mention my own work with Zahn, where, we developed this concept a little further. So in these cases, they're just talking about, X, and the special fiber is our gives us the pair. But we wanted to, we were looking at a case where X itself has some boundary, over the generic fiber, and then this, this we can extend to pairs over K, xk delta K. And here, it's really just the same definition. What's remarkable is like the properties still hold. So let's see. So the essential skeleton, I'm not going to give you the exact definition, but let me just tell you what it does. So this is a subset of Xn, and it corresponds to the dual complex of a DLT of the special fiber of a DLT minimal model of X over R, assuming one exists, because in this case we can't use BCHM because R R might not be like a Noetherian ring or something, or that's not the. Yeah, that's the point, is that R might be like the power series ring or something, and so you don't have finite generation statements. So that's just like a minor technical note, but we expect all of that stuff works, and there's some there's some special extra cases worked out, but it's just kind of, we have to write that part of the fine print. Okay, so let me just give an example of what's going on here, rather than spell out the definition. Okay, 20 minutes in. All right, so for example, well, we have a valued field, so let's just think of that valued field as the formal Laurent series. So you just take the formal power series and then you invert T's to make it a field. And then, this is kind of my favorite example, because it really kind of illustrates the interesting topological things that show up, is if you take xyz plus t times x cubed plus y cubed plus z cubed. And then this is all living inside P2 over K. And so here, it's easy to, so here, let's just look at what's happening here, is that if you let t be 0, as t approaches 0, you're just getting the 3 hyperplanes. So the idea is that over 0, you just have 3 lines in P2. So, if you just extend this to R coefficients just by using the same equation, there are other R models, but this is like an easy one to write down. And it turns out this model is also a nice one in it being a DLT minimal model. And then, when T is generic, well, this is a smooth curve, so you get a smooth curve. So you get like a degenerating family of smooth curves, over the generic point. And then here you get the special fiber. You have 3 P1s intersecting in this way. And if you look at the dual complex here, well, the dual complex is a circle topologically, because you just have, you get the triangle. You get, if this is, you can call these 1, 2, and 3. And the dual picture is that I have a point corresponding to 1, a point corresponding to 2, and a point corresponding to 3. And then these are connected up according to their intersections. Okay, so then what does XAN look like, and what is the essential skeleton? All right, so yeah, unfortunately I don't have a lot of board to work with, so I'm gonna erase this, but I didn't really tell you anything very informative there, so it's probably not a big loss. Okay, so the idea is that XAN is a valuation space, so it's it's a bunch of valuations on the the various function the various residue fields of X, but the major part is where that field is just the function field, and so that becomes big because there's a lot of ways of putting a valuation on the function field. So these are called the birational points of the Berkovich space, and the idea is that anytime you have a divisor in the special fiber, that gives you you can just take vanishing along that divisor, that gives you a valuation, and you can scale it so it extends the one on K because you're actually supported in the special fiber. That's where that condition comes in. And so the idea is that this dual complex shows up inside the Berkovich space, because I can just take 1, 2, and 3, and then I can interpolate between them using monomial valuations. Okay, and then there are other things I can do, like I can just pick a point, and then I can blow up. And if I blow up at that point, that gets me a new valuation that sticks off from here, because if I imagine blowing up in this total family, the next thing I get is I just get something sticking off like that. And so that gets me, if this was in 1, that gets me a new valuation out here, along with monomial valuations interpolating. And so that's why, and you can imagine I can repeat this process as much as I want. And so then this thing, it grows off into this crazy infinite graph. But then the non-trivial homology of this graph is just in this cycle here. Okay, and so then, and then you could also, you could imagine blowing up between 1 and 3, and then blowing up again along that curve. And so then you get this crazy picture, which is hard to visualize, but of just this infinitely branching graph, which in the case if we had had a P1 instead, it would just be an infinitely branching tree. But because this is this elliptic curve with genus 1 curve with multiplicative reduction, we get a cycle here. Okay, so what's going on with the essential skeleton here? Because that's what I promised to tell you about. Well, the idea is the essential skeleton is just going to be this this circle in the middle. And so the idea is why is that? Well, what's happening here is that you can imagine, so you think about this family, this is a family of genus 1 curves, so it's K-trivial, and the special fiber is trivial. So if I think of delta as just being the special fiber, then I have this condition here. And then the things that are showing up in delta, so then the dual complex I'm interested in is just the dual complex of delta. So that's just the cycle here. But then the claim is that this is birationally invariant. So let me show you what happens when I do blowups. So I could choose to blow up at an intersection point, let's call that P, or I could choose to blow up at not an intersection point, let's call that Q. So we've seen that if we blew up Q and tried to extend the complex, it would create an extra piece here, which we don't want. Whereas if I blow up at P, it's just subdividing this circle. So it's not really changing the topology. It's not changing which valuations I get. It's just changing how I combinatorially divided them up. Okay, and so the idea is that, well, if I blow up at P, then what I get is I get the Kx, xp plus the strict transform of delta, plus EP, that's still trivial. So then the idea is that EP shows up with coefficient 1 on this side, and the contribution on this side, which would be the log discrepancy, is 0, so it shows up in the essential skeleton, and it shows up here. So this one is P, this is EP, this is EQ. And so then if we blew up at Q instead, hopefully you can see down here, then, because that's only on one of these divisors, then I actually get an EQ on both sides. And so here, the log discrepancy is going to be 1, and it doesn't show up in the essential skeleton. Okay, so that's part 1. Any questions? I think this is a good place to pause. Okay, so the ultimate goal is to use this to investigate a little bit the birational geometry of moduli spaces. But before I get into that, I have to tell you about tropical compactification. Okay, so first let me tell you about tropicalization from this perspective. So the idea is if we instead have, some U that's a subvariety of a torus, and this guy, we'll think of it as spec of C adjoint Z1 plus or minus up to Zn plus or minus. And then the idea is we have this tropicalization map which sends the analytification to NR. So you remember this analytification, this is just the space of valuations. So how do we go to NR? Well, it's like sending, this is the co-characters, but I mean, you can really just think of this as R to the N if you like. And, well, how do you get this NR, something in this NR? Well, NR is just valuations on, on the Z's. It's the co-characters. So you just say, well, I just plug the Z's into this, to whatever my valuation is here. That gets me my numbers, and it lands me in NR. That's what tropicalization is. So we just send a valuation V to whatever it is on Z1, Z2, up to Zn. Okay, and so then this gets you, some combinatorial object in NR. And let me, I had this example prepared. I don't know if I'm going to run out of time if I present it, but I think it's better to present the examples than the theorems generally. So I'm going to present the example. And so the example is just let's imagine we have P2 with the coordinate lines removed, except we remove one more line. So, I'll have my A2, which is just P2 with line infinity removed, remove the coordinate axes, and then I remove this line. And then I want to say what this looks like tropically. What's the tropicalization of this? So now this U is equal to A2, and I remove, the vanishing of X, Y, and X plus Y. This is not great notation, but whatever. And so if I wanted to write down the coordinate ring of such a thing, I'd have, so I would write this as Z, I'd have my Z1, Z2, and Z3. So I need a third invertible coordinate corresponding to the fact that X plus Y is now invertible. So these correspond to X, Y, and X plus Y. And so then I have to mod out by Z3 minus Z2 minus Z1. Okay, and so if I want to tropicalize this, so the tropicalization is actually intrinsic because this U, it lives in kind of canonically inside a torus because it's just, you think about all the units in its coordinate ring. So the idea is that if I want to look at the tropicalization points in tau U, so this corresponds to choices of V of Z1, V of Z2, and V of C3, where this is allowed to be 0, well, that means that the two with the lowest valuations have to be tied, because otherwise the valuation of this quantity would just be whatever the one with the lowest valuation is. So for this to be 0, that means these two of these have to be tied. So the lowest valuation tied. Okay, and so this is just saying that you have V of Zi equals V of Zj, and that this is less than or equal to V of Zk, and then you allow every permutation. Okay, and so then if you look at this, this is in some three-dimensional space. Well, you have, I drew the angles a little off. Let's try and fix that. There we go, that looks better. Okay, and so you get this object in R3, and so this is like 1 equals 2 and it's the smallest, 2 equals 3 and it's the smallest, 1 equals 3 and it's the smallest, and these all fit together. But the thing I want to do with this is it looks like a fan, right? Well, it's not a fan yet because you have to break it apart into pieces, but if you subdivide this a little, then you can give this the structure of a fan in this space, and fans give you ways of partially compactifying this torus. So then what you do is you do the partial compactification, take the closure of U inside, and what do you get? Well, the idea is that this fan, it's the fan of P2 if you don't fill in the coordinate points. So this is minus, coord points. And then you cross it with P1 because I'm going in the other direction. And that P1 corresponds to the blow up here. So the picture that you get so we compactify the torus using the fan, and then we take the closure of U inside. Well, what do we get? Well, the P1 corresponds to the P1 of lines through here. So what I get inside this P1 cross P2 is just the image of the birational image of this P2, which is an F1. So the idea is that this is a copy of F1, and then I'm missing the line upstairs at infinity. I'm missing the line at 0 that's the exceptional divisor, and then I'm also missing the 3 lines, so these all form the boundary. And so what you see we've done is we resolved the fact that if you just compactify this in A2, these intersect poorly. This isn't a good intersection because you have 3 divisors intersecting in one codimension 2 locus. Whereas here, doing this compactification fixed the problem. And this is tropical compactification. So this is this technology is due to Tevelev, and I'm like, yeah, I think I haven't given a talk in a while, so I wasn't kind of mindful of my time, but so I have a lot more to say, but I'll try and sort of cut it down to get to the important stuff. And this is idea due to Tevelev is to compactify the variety this way, is that if you're inside a torus, the right way to compactify is to take the tropicalization of your variety, put a fan structure on it, and then partially compactify the toric variety that way, and this compactifies your variety in a nice way. In particular, so this procedure will always produce U bar with a reasonable, let's say, a reasonable stratification, which I don't want to say what that means. Okay, so let me state the main conjecture of my talk, which All right, so to be honest, I'd been thinking about this for a while, and I thought this was something that people knew, and so I never wrote it down. But then I thought about it now for this talk, and now I'm like, okay, I don't know how to prove this. So although I'm quite sure some version of this is true, because it's also then when you have a thing that you think it's true, you have to worry about getting all the hypotheses right. So I'm just going to state this as a conjecture because I feel like that's the most honest way to talk about it, even though I'm very confident something like this is true. Okay, so conjecture. And I think at a conference I once mentioned this to Tevelev, and he was like, oh yeah, of course that's true, but I don't know what exactly I told him, so if this is false, don't blame him, blame me. So the idea is that if you have a pair x delta such that if I remove the boundary, I get something very affine. That just means that this is a subvariety of a torus. So let's say is a subvariety of a torus. And if I take the tropicalization map restricted to the essential skeleton of, I don't want of x, I want it of u, equivalently of the pair x delta. If this to the tropicalization of u is an isomorphism, or let's say a homeomorphism is probably better, then U has a tropical compactification which is a DLT, or some singularity condition. I mean, this is kind of the most important part, but it's also the most speculative part. This is some sort of minimal model for x delta. Okay, so for various reasons, I strongly suspect something like this is true, because it's well, if this wasn't, if this was, the idea is if this is a bad map, then you have all these extra valuations that are supposed to appear in the middle model that don't show up in the tropical compactification. So the idea is that if this is a good map, then the tropical compactification gets you exactly the valuations you need and none others. That's the idea here. And so what was the motivation for this? Well, the motivation is really looking at moduli spaces of hyperplane arrangements. So anyway, there's a whole story about this that I can't quite tell you because of time constraints, but so let's let XRN equal the open moduli space of n hyperplanes in PR minus 1. That's supposed to be an R. And then we say that XRN bar, this is the tropical compactification, or a tropical compactification. And it turns out that for some tropical compactification, this is exactly what you want, namely the KSBA space. Well, not the entire KSBA space, but it's some component. This is something I think which is not well understood. This is a component of the KSBA space, which is the one that parameterizes stable pairs. So the idea is that you have n hyperplanes in PR minus 1. If they're just hanging out in their in general position, that's great. But then you can move them so that they're not in general position. They can collide. They can intersect too much. It's no longer a stable pair. You have to alter it to get one where the where the surface, or whatever you have with its boundary is log canonical, and kx plus delta is ample. Okay, so all of this is work of Hacking, Keel, Tevelov in various combinations. Let's just use commas. And then also, this is all based on work of Kapranov and Laforgue. So, there's probably a lot of other names that I'm not mentioning here, but these are kind of some of the major ones. And just, let's just say that when r equals 2, we get, well, what do we have? We have n hyperplanes in P1, that's n points in P1, that's M0n. So we actually just get God's honest M0n bar with the boundary. The standard, Knudsen, Grothendieck, Lean-Mumford compactification. Okay, so, all right, now, okay, so we have 5 minutes left. So let me get to the punchline here. So why do all of this? So one thing that's always kind of mystified me about the moduli space of curves is that the moduli space of curves parameterizes like log canonical models of curves, right? In the sense that, if you have a curve, maybe, it's MGN, so you have a boundary, and then it's a log canonical model that pairs what you're getting parameterized around. It's like the canonical divisor is ample, which is, what we want to parameterize. And if you look at the moduli space itself, it's also a pair, and that pair is also a log canonical model. But this is no longer true when when r gets bigger. So why is that? So like I just said, if I take M0n bar with its boundary, this is a log canonical model. Okay. So in particular, that says, that k plus the boundary is ample, and the singularities aren't too bad. Okay, but so Murphy's law, as in Murphy's law for moduli spaces. So this comes from Minev's universality theorem. This applies for even for r equals 3, if we're looking at x 3, 9, and worse. So for if this 9 becomes any bigger, what happens is this becomes too singular for this to hold. And so, the authors, especially, Hacking, Keel, and Tevelov, they've been very interested in this because this Murphy's law says that you get every singularity. And so then they're saying, okay, well, if you had some way of constructing log canonical models of these things, then you would have a way of partially desingularizing kind of arbitrary singularities, which is a bit crazy. So they were, but what I'm proposing is that, all right, well, if my conjecture that I stated previously is true, then you can get at the log canonical model of these guys by studying the essential skeleton, which is still a pretty, that's a pretty tough chore because, this is living in this crazy valuation space, but it's still it's another handle on this problem. Okay, so, so to approach this, we really, we want to start with r equals 2 because, if we can't do it for M0n, then it's just hopeless in general. So there's this very nice paper of Cueto, Habish, and Werner. And, for M0n, they're really talking about the Grassmannian, but it's, equivalent. They define a section of tropicalization So the idea is you have tau from the analytification to the tropicalization, which, if you know this story, this is more commonly referred to as the tropical Grassmannian. The relation with the Grassmannian is that if you take the open locus of the Grassmannian, where all the Plücker coordinates are non-zero, and you quotient out by the torus that scales the Plücker coordinates, then you get M0n. And then, there's this whole story of Chow quotients, but the tropical geometers think of this as the tropical Grassmannian. This actually parameterizes phylogenetic trees with it's with a Y, yeah. Trees. So these are like some trees with metrics and distances, and they have n leaves. And then the idea is that we have this sigma that goes back, and so then the natural, the sort of the conjecture I've led you to think is that, well, you would hope that the image of this section is the essential skeleton of the pair M0n with its boundary, and that is exactly what my student Zhishang Xu is proving in his thesis. So theorem. I suppose this is, I guess, yeah. I mean, you have a proof already, so this is. I guess I haven't looked over all the details myself, but I believe in this theorem that the image of sigma is the essential skeleton of M0n. Okay, and I think that is a good place to stop. So thank you for your time and attention, and any questions? Yes?
What happens when r equals 3 and n is smaller than 9?
Oh, yeah, great question. Yeah, so then I believe, I think Kiel and Tebelev have a conjecture there that it is the log canonical model for, let's see, so the thing here is that for the interesting ones are 3.6, 3.7, and 3.8. Because 3.5 is just, you can do a duality and it becomes 2.5. So it's like really these are kind of the exceptional ones, and these are conjectured. It's conjectured that everything works out and you get the log canonical model. Yeah, so I also asked Zhishang to think about this 3.6 case a little bit and kind of do some preliminary computations of working out what these surfaces that show up in the compactification and the boundary actually look like.
Other questions? Okay, we'd like to once again thank the speaker, and the next talk will be at 3 o'clock.